Okay, in the previous video I ran a two-group MANOVA comparing two groups of students, or high school students, on their plans concerning attending college during the first year after graduation. So we had group one that was basically representing those individuals who plan to attend college, and group two contained those individuals who did not plan to attend college. And we were basically comparing the groups on measures of academic self-efficacy, perceived utility of college for their futures, and intrinsic motivation for learning. So just quickly as a recap, just to kind of show you the comparison, the two group MANOVA. If we go to Analyze, General Linear Model, Multivariate, I've got my independent variable in the fixed factors box, my dependents in the dependent box. I'd asked for grand mean and means for each group, descriptives, effect size, power, homogeneity tests, and the like. And then so when we ran the analysis, we saw that in terms of the multivariate effect for plan, we saw, just kind of using this Wilks lambda line right here, we saw that there were significant group differences on the set of dependent variables. And we also saw that we had a pretty good effect size for that analysis as well. Let me also note, too, I guess I'd forgotten to mention this in the previous video, but I'll go ahead and mention it now. As a follow-up to, I talked about in the previous video, one follow-up to the MANOVA is the test of between subjects effects, and these are basically all one-way ANOVAs comparing the groups on self-efficacy, utility, and intrinsic motivation. And this is ignoring the intercorrelations among the dependent variables. And so, we had seen that there were no group differences on self-efficacy. We saw significant group differences on utility and significant group differences on intrinsic motivation. And I think I'd forgotten to mention that up here where you had Levene's test, these are basically tests of homogeneity of variances related, and so this is basically applied to each of these tests down here. So in other words, each analysis of variance assumes equality of variances between groups, and so you can see right here that our p-values were all greater than, say, 0.05, suggesting that we had equality of variances for each dependent variable between the groups. So this is, these results right here are interpreted and utilized in relation to each of these ANOVA tests that we see right here. So that was just something that I'd failed to mention in the previous video, and I think I wanted to go ahead and mention that here. So at this point, we had seen that there was a significant effect of our planned variable on the set of dependent variables. Like I said, when I say effect, I'm not meaning it in a causal sense necessarily. I mean it more in a predictive sense. Now what we're going to do is we're going to run a discriminant analysis comparing the groups, or basically looking at group differences in a little bit different way. So in discriminant analysis, what happens is, if you're using this as a follow-up to the MANOVA, the dependent variables that were in the MANOVA actually become predictor variables in the discriminant analysis. And the grouping variable from the MANOVA actually becomes the dependent variable. And so what we're basically doing is we're comparing the groups on the linear combination of those dependent variables. And the linear combination is basically referred to as a discriminant function. So I'm not going to spell this all out because it's really hard to write with this little pen tool here, but we'll just say it's a discriminant function. So, and a discriminant function is really nothing more than a latent variable as a composite of the information that's contained in the original set of measured variables. So we essentially are going to take this discriminant function and we're going to compare the groups on that discriminant function, and not just compare it, because really we've already done so when we looked at the multivariate tests. When we look at these test results right here, we've already essentially compared the groups on the discriminant function. But what we would also like to do is to describe the discriminant function. So we can actually, so this is kind of the nice thing related to discriminant analysis, is that we can describe the dimensions on which the groups actually differ. In the case of a two-group MANOVA, there is actually only going to be one discriminant function. If we have more than two groups, then there's actually a little rule that determines how many discriminant functions there are, meaning that the groups could groups could actually be discriminated on more than a single discriminant function, and so that will be for another video. But in the case of a two-group MANOVA, if we're following up, there will only be one discriminant function that will that the groups can be separated on. So let's run the discriminant analysis. So we'll go to Analyze, to Classify, and then down to Discriminant. So we put our grouping variable plan into the grouping variable box, and we have to define the range. So the minimum and maximum values are basically 1 and 2, because those were the only two values that we had. So we'll click on Continue, and then we'll move our former dependent variables over to the independence box. So this is very much like a regression analysis with a dependent variable that is categorical. And in fact, this is very much analogous to what we were doing with, this is very much analogous to what you might do with logistic regression. Except, you know, with the logistic regression, the assumptions are less restrictive than discriminant analysis. So in discriminant analysis, you have assumptions such as multivariate normality concerning your independent variables. You also have assumptions related to equality of variance covariance matrices, just like what we had with the MANOVA. At any rate, under statistics, we can ask for really a lot of the same information that we got when we ran the MANOVA. So we can ask for the means, the univariate ANOVAs, which were the default follow-ups to the MANOVA test in SPSS. You have Box's test, which assesses that assumption of equality of covariance matrices. And in fact, what we'll see is that all these results will be exactly the same as what we had generated with the MANOVA. You can also see within groups correlations, so you can actually get a better idea about how the dependent variables were correlated originally and with the MANOVA, and how essentially the predictors are correlated for the discriminant analysis. These, you know, they're exactly the same. Function coefficients, you've got, you know, Fisher's and unstandardized coefficients here. So basically, these are kind of capturing unstandardized relationships between the predictors and the discriminant functions. Under Classify, because we have unequal group sizes, we're going to click on Compute from Group Sizes. This is one of the interesting things with discriminant analysis. You can actually not just be interested in sort of describing the discriminant functions. You might actually be interested in using discriminant analysis to develop a decision rule for classifying cases in terms of the probability of group membership related to a dependent variable. So, you know, right now I'm talking about discriminant analysis mainly as a follow-up to MANOVA, but it actually can serve as its own standalone procedure as well. So you don't necessarily have to run a MANOVA or run discriminant analysis as simply a follow-up to the MANOVA. You can run discriminant analysis as its own standalone. So we can also ask for a summary table, which would give us an idea about how well the model is predicting group membership based on the set of predictors. So again, this is very similar to what you might see if you're running logistic regression. So now I'm going to click on Continue, and just to kind of show you what I mean by predicting group memberships and so forth, if you click on Save, you can actually ask SPSS to kind of save predicted group membership to the SPSS file. The discriminant scores, these are basically individual scores on the discriminant function. And like I said, the discriminant function is a composite variable that is generated from the set of predictor variables. So it's very much like predicted scores on Y in the context of multiple regression. So we have basically discriminant scores, and then we also can ask for predicted probabilities of group membership that are based on those discriminant scores. So you don't have to click on these. I'm just going to just use this to show you what I'm talking about. So we'll click on Continue, and then we can click on OK. So looking at our output, you can see you've got really all this information is exactly the same as what we had seen previously with the MANOVA. These are the one-way analysis of variances comparing the plan groups on each separate dependent variable. So this is, it's a little drilled down, but these are the basic test results that we saw previously following the MANOVA. So these are the univariate ANOVAs. You can also see right here the pooled within groups correlation matrices, and you can see the correlation between self-efficacy and perceived utility across the two groups was 0.085, so really a negligible relationship. You saw a positive relationship between self-efficacy and intrinsic motivation, and also a positive relationship between utility and intrinsic motivation as well. So, like I said, particularly because you have this correlation between utility and intrinsic motivation, if you just look at these univariate results right here, you end up reanalyzing some of the same variation in these variables because of that correlation between those variables. So now, if we scroll down, you'll notice that you also have boxes test, which is exactly the same as what we saw previously with the MANOVA results. So the value is exactly the same, no big surprise there. Which now leads us to the next part of our SPSS output, and you have the summary of canonical discriminant functions. And so, like I said, the discriminant function is a composite variable that is formed from the information that was contained in the set of predictors, which formerly, in the case of MANOVA, had been the dependent variables. So you'll notice that, first of all, you've got function 1, and that's in the case of a two-group MANOVA, you're going to have only one function. Where you have more than two groups, you will have two or more functions, and again, that is for another video. But at any rate, we have what is called the canonical correlation, which is the correlation between the grouping variable and the discriminant function. So the canonical correlation will range between 0 and 1. And obviously, as you get closer to 1, you have a stronger relationship that is being manifest in terms of the relationship between the grouping variable and the discriminant function. So, concerning the one thing to kind of note is that, kind of going back to our canonical correlation, actually, if you square it, if we just take 0.78 and square it, then basically it gets you 0.6084, which is actually going to equal the partial eta square value that we had with the with our MANOVA. So there it is right there. So again, that's just reflecting the relationship between our independent variable and the set of dependent variables, and more specifically the linear composite of the dependent variables. So as you can see, that is what the partial eta squared was getting at previously. So again, we have really a strong relationship between the grouping variable and the discriminant function. The next, the Wilks lambda test that we have right here is a test basically addressing the significance of the canonical correlation, at least as it relates in the two group situation. So you'll notice that the Wilks lambda value that is printed out right here for test of function 1 will also be exactly the same as what we had previously in our MANOVA results, which was 0.392. So again, there it is. So the test of that function was statistically significant Once again, that just basically is indicating that we have a significant relationship between our grouping variable and our discriminant function. Next, you can see, we'll just kind of go down just a bit here, and you'll notice that you have standardized canonical discriminant function coefficients and a structure matrix. And a structure matrix is nothing more than the correlations, or involves the correlations between each of our predictor variables in the model and the discriminant function. So in judging the correlations, there are various rules of thumb. One rule of thumb is, if you have a structure matrix correlation, or a correlation between the predictor and the discriminant function that is equal to or exceeds the absolute value of 0.30, or sometimes I've seen 0.33, then you would utilize that to help to describe or name the discriminant function. So the structure matrix is utilized in a way that's very similar to what you would utilize factor loadings in factor analysis, which is to say that you utilize those factor loadings in order to name the factors in the model. So here we see that perceived utility is, is very highly related to the discriminant function. Intrinsic motivation is also highly related. Self-efficacy is not really very related. So, really, if I was naming this discriminant function, I would not think to include self-efficacy in the naming process. So I might think about, basically, if I was going to name this function, I might name it something like value or perceived value related to schooling in general. So that's just my name. You might see something else that theoretically that might make sense to you, but I'm just going to name it this for the time being. The standardized canonical discriminant function coefficients are very much like the beta coefficients in multiple regression, which is to say that it allows you to assess the relative contributions of the predictor variables to the discriminant function. So this can also be useful in terms of naming the discriminant function, or just if you want to just talk about which variables are their relative contributions to the discrimination between groups, you can do so. So we have, in this case, we have utility has the highest standardized discriminant function coefficient, followed by intrinsic motivation. So really, the discriminant function is largely being defined by the utility variable. So you can see it here and you can see it here. And intrinsic motivation is contributing somewhat to it, but relatively speaking, it's utility that is really driving that discriminant function. And self-efficacy, again, is not really contributing much, if anything, to that discriminant function. So once again, I'm going to name the discriminant function value, and now I'm going to scroll down a little bit. Basically, this chart right here is our table right here is giving you the unstandardized function coefficients, and this is basically these are the coefficients that, when multiplied by the scores on each of the predictor variables and then summed together, there's the intercept, by the way, then that actually gets you the discriminant function scores. So this is the actual way in which the or the manner in which the discriminant function, these are the coefficients used to compute the discriminant function scores for each case. So, really quickly, to kind of show you what I'm talking about, you have, kind of going back to the data set, we have the discriminant function scores right here. So as you can see, these are each person's discriminant scores based on that particular model. So you can see, you have a number of positive values right here. You've got a negative value right here, and you'll notice that really a lot of the positive values, not all of them, but a lot of the positive values were assigned to group 1, or predicted to fall into group 1. You had smaller values and negative values that were predicted to fall into group 2. So at any rate, if we go back, you'll notice this table right here where it says functions at group centroids. So basically these are nothing more than multivariate group means. Okay, so in a nutshell, this is the mean for on the discriminant function for those individuals who plan to attend college. This is the mean on the discriminant function for those who planned not to attend college. So you can kind of think about it in terms of you can see that if we had named our function, remember we named our function value. So in other words, those people who planned to attend college had higher value scores than those who planned not to attend college. So that is basically how we would interpret the functions at group centroids chart right here. There's basically the discriminant function mean was higher on valuing for those who plan to attend college as compared to those who planned not to attend college. So kind of scrolling a little bit more, now we have at the bottom, like I said, we can utilize discriminant analysis in order to predict group membership, and then we can also look to see how well our predicted group membership fits with the actual group membership observed in the data. So if we go back to our original data set, we had asked for, one of the things that we'd asked for was predicted group membership. So these are predicted group memberships, and this is formulated based on those discriminant scores. We also have a variable that's basically the predicted probabilities associated with those group memberships. So this is the probability of membership in group 1 for our analysis, and you can see right here these are the probabilities for membership in group 2. So if you add across these two probabilities, you would end up with a probability of 1. So you can see that for the first case, based on their discriminant scores, the predicted probability of group membership was 0.99 to be in group 1, and hence they were categorized or predicted to fall into group 1. When you see that, let's kind of go down, the probability for this person of being in group 1 was 0.345, and the probability of being in group 2 was 0.655, so you can see that that person was predicted to fall into group 2. So when we look at our classification results, we can look to see how well or how accurately the model predicted who fell into which group. So you can see right here that we have original counts, and then we have predicted group memberships. So you can see that of those who actually planned to attend college, we had 30 individuals who planned to attend college. We had 24 of them that were predicted by the model to plan to attend college. So we had an accuracy rate of 80% in terms of correct classification of those planning to attend college. We had 6 individuals out of the 30 who basically who actually did plan to attend college, but who were predicted by the model not to plan to attend college. So we had a miss rate of 20% here. We had 39 individuals who planned, out of a total of 43, who planned not to attend college, and we had, basically it was 39 individuals who were predicted not to want to or not to plan to go to college, and who actually did not plan to attend college. So we had an accuracy rate here of 90.7%. And we had, of those 43 individuals who planned not to attend college, we had 4 that were predicted by the model who planned to attend college. So we had a miss inaccuracy rate of 9.3%. So in other words, on this primary diagonal right here, these values represent hits. So this represents accuracy in prediction. What we had on the off diagonal here basically were misses in terms of accuracy rates. So, or another way of putting this is that we had essentially basically a false negative rate of 20% concerning those attending college. So in other words, 20% of those who actually did plan to attend college were categorized as not planning to attend college. We had a false positive rate for those who actually did not plan to attend college and who were predicted by the model to want to or plan to attend college. It was 9.3%. So overall, what we see is a classification accuracy rate of 86.3% based on the set of predictors. So actually, this is pretty good in terms of predicting group membership based on the model. But clearly, the model does a better job of predicting the choices of those people who actually did not attend college as compared to those who plan to attend college. So at any rate, that sort of sums up the discussion of discriminant analysis, and in particular discriminant analysis as a follow-up to a two-group MANOVA.